Hello everyone, welcome back. So this is the lesson number 5 of a series Fundamentals of Material Science. In today's video, you are going to learn how you can apply material balance when there are multiple unit processes involved in your problem. So let's get started. Well, so far you have learned how you can apply a material balance on a single unit process, such as distillation, column, reactor, and mixture. But in reality, there is always more than one unit processes combined to achieve the desired product. As an example, you can see here the ammonia process flow diagram, and here you can see several different kinds of unit processes are combined to produce ammonia. Here you can see the primary reformer, secondary reformer, heaters, adsorbers, strippers. So all of them are involved in just one process, that is the ammonia synthesis process. So in practical applications, you have to apply material balance on such kind of processes, and how you can apply material balance on these complex processes. So that is the topic for today's discussion. So we can move forward. So first of all, we have to understand one basic definition that I'm going to use to solve the model problem for this lesson. That is, what is a system? A system is any portion of a process that can enclosed within a hypothetical box that we called it boundary. Okay, so how we are going to use this, you will see in few minutes. Okay, so here is the example for today's discussion. So here we have two hypothetical unit processes, number one and number two. These two rectangle are two square. Okay, so here we have two component A and component B, that are entering first into the first unit, and some of them are leaving, and then rest of them are moving, where another stream is mixing, and then it's entering into the second unit process, and then we have two outlet. So this is the problem that we are going to solve or discuss to understand how you can apply material balance when there are more than one unit processes involved in the given problem. So first of all, we have to define the systems on which we can apply a material balance, and for that I already have taken this screenshot of this problem. So here you can see these dotted lines. So these are called the boundaries. Okay, so this is the overall system boundary, this one, and then we can also apply these hypothetical boundaries around each unit process. So these are called subsystems. So this is the overall system, then this is the subsystem, and here where these streams are mixing, so this point is also act as a mixer. So here we can also apply a sub boundary, or we can also call it subsystem, and similarly on the second one. So here we have four different boundaries. One is the overall system boundary. So the second one is on first unit process. This third one is on the mixing point, and the fourth one is on the second unit process. So the way forward to solve such kind of problem is, number one, you have to perform degree of freedom analysis. Okay, to see either we can solve this problem or not. And where you are going to do this degree of freedom analysis, first you have to do it on outer boundary, that is the overall system boundary. So in if we consider this overall system, so we have here two input. So this is number one, this is number two, and here we have three output. This is one, this is two, and this is three. So considering that fact, we can see what is noun and what is not noun. So here we can see, here we have two unknowns, okay, and here we also have two independent equation from species balance, species A and species B. So two unknown minus two balance equation. So the degree of freedom on the overall system is 0. So this can be solved. So the first we can solve for these unknown variables, that are the mass flow rate going out in the stream 3, and also the mass fraction of component A, and then you can calculate the mass fraction of component B. So this is the first thing, and after that you have to do the same thing on the mixing point. So this is the mixing point here, okay, and here if we see how many unknown we have, here we have 1, 2, 3 and 4. So we have here 4 unknown, but we can have only 2 species equations that we can write here. So here we have a degree of freedom 2. So we need at least 2 more informations, or we need 2 more independent equations to solve this particular point. Okay, so similarly, if we see on a unit operation 1, that is this one, here we have 2 unknown, okay, so 2 unknown, but we also have here 2 equations that we can write on a species A and species B, and here we will also have a degree of freedom 0, so that can be solved easily. And if we move to the unit operation 2, and here how many unknowns we have, so this time maybe you can just stop or pause the video and try to figure it out by yourself. So here we also have 1, 2, 3 and 4 unknown, and again we have only 2 independent equations from the species balance, and so again we have a here degree of freedom is 2. So after having the degree of freedom analysis, we are in a position to solve this problem. So how we can solve all these unknown? The way is, first we have to apply overall material balance. Okay, so if we see the overall material balance, we have here 100 kg, that is the input, 100 kg per hour is entering, and here from the stream 2 we have 30 kg per hour that is entering to this system, and that is equal to, let me see, yeah, so in the stream from unit operation, unit process 1, we have a output of 40 kg per hour, plus from here we have 30 kg per hour, and plus M3 kg per hour. Okay, so when we solve this problem, we can have a M3. Okay, so the mass flow rate of this stream, that will be equal to, if we solve this, it will come out 60 kg per hour. Okay, So when you have this one, after that you can apply the you can apply the material balance on the unit process one here. Okay, so if we apply a balance on one, it is going to be 100 kg per hour. That is the input. And what are the output? 40 kg per hour and M1. So 40 kg per hour plus M1, that is the molar flow rate of this stream, and it will come out as also 60 kg per hour. Okay, so after that you can apply a balance on a species. Okay, for example, if I write the overall balance, so on a species A, if I apply overall balance, so it will be 0.5 multiplied by 100, that is in from this stream. Okay, and from this stream, what we have here, 0.3, that is the mass fraction of A multiplied by 30, equal to, so this is the input, and what is the output? And output we have here 0.9, that is the mass fraction of A multiplied by the total mass flow rate, that is 40 from this stream. Okay, and plus from this stream we have 0.6 multiplied by 30, 0.6 into 30, and also plus, that is this unknown stream, but here we already know the M3, that is a 60, and we don't know the mass fraction of A, so that here it's given as x3. So from here we can have the mass fraction for x3, that comes out, if you solve this equation, 0.0833. Okay, so when you have x3, you can easily calculate 1 minus x3, so it will be the mass fraction of B in this stream. So it is 1 minus 0.0833, and here you have a mass fraction of B. Okay, so similarly, when you I just write the species balance on the overall system, but we can also write the same species balance, but on only on unit the first unit of unit process, that is here, number 1. So I will change the pencil color to red, and I'm going to apply a species balance on unit process 1, and here I can write on species A, 100 is the total mass flow rate that is entering. Okay, multiply by mass fraction 0.5, so this is the input to this unit process, equal to the output. And what is the output here? Here we have 40 is the mass flow rate from here. Okay, and 0.9 is the mass fraction, plus this is the output if we only consider unit operation, unit process 1, sorry. And here we already calculated this M1, that was 60. Okay, mass flow rate. And what is the mass fraction? That it's given as x1 for A. So from here we can have x1. Okay, if we solve this equation, and when you have x1, you can calculate 1 minus x1 as a uh, mass fraction of a component p. Okay, so when you have these values and the data, then for this mixing point, the degree of freedom will also become 0. Why? Because then you have only two unknown, that is m2 and x2, and you can write two independent equation and you can solve this particular mixing point. So in this way you can solve very complex problems, but you have to solve it systematically. So the procedure is, first you have to do degree of freedom analysis first on the overall system and then on each subsystem, and then try to solve from the overall system to minimize the number of unknowns, so that the points where the degree of freedom is higher than 1, you can minimize the degree of freedom at those particular point equal to 0. So that's all for today's video. I hope you like this video, and if you understand or if you learn something new from this video, please don't forget to like, share and subscribe to the channel. Until next video, take care. Bye bye.